So in the earlier lecture, I talk about angular velocity, angular displacement, and angular acceleration. Now, in this lecture, I will talk about some few more important terms which are important in which are important in rotational motion. So first of all, let me recall inertia, and then I will talk about the moment of inertia, right? So inertia means what? Inertia is a property or the tendency of an object that resists any change to its state of rest or motion, and it basically depends upon the mass. So let me try to write down its basic idea. So inertia can be described as a property or tendency of an object that resists any change to its state of rest or motion. Right. Inertia, and in the word inertia comes from the word inert. Inert means the thing will remain as it is, right? And we have to do something to change its position. So if it is in the rest, then it will remain in the rest, and if it is in motion, then it will remain in the motion until unless we will apply some external force on it, right? So this is the meaning of inertia. That means if body is in motion, then to stop it, I have to apply certain force. Similarly, when some object is in rotation, it is rotating about some axis, and it tries to remain in that state until unless we will apply certain force on it. So that means, similar to inertia, we will define a new term that is known as moment of inertia. We will define a term, moment of inertia, for the rotational motion, right? So let me write down that moment of inertia is the measurement of an object's resistance to change its rotation. And here in inertia basically depends upon the mass, but in case of moment of inertia, it depends upon the mass and distance from the axis of rotation. For example, for the case of inertia, if we are having two bodies whose mass is m and capital M, such that capital M is greater than small m, then its inertia will be larger in comparison to object whose mass is lesser, right? But here, in this case, we are having two objects, or the two masses, or so sorry, not masses, but suppose we are having a axle, right? And about this axle, this is one diagram and this is another diagram which I am considering. Then mass of these two wheels is same, its mass is also m and its mass is also m, but its mass is concentrated over here. That means it is at a larger distance and it is at a smaller distance. Then this must have large moment of inertia as compared to this, right? That's the meaning of it. So that means uh, this moment of inertia depends upon the mass and the distance from the axis of rotation, right? So that means this must have the large moment of inertia in comparison to this, because both have the same mass, but the distance will be smaller here and its distance from the axis of rotation, or axle, it is the axle about which this wheel is rotating. So that means in this case moment of inertia will be larger. So it is the wheel 1 and wheel 2. So both have same masses, but the distance is the d1, and here the distance is d2 from the axle, and d2 is greater than d1. Then moment of inertia of wheel 1 is lesser than the moment of inertia of wheel 2, right? That's what we are concluding from here. Now, let's try to look at it mathematically, that how do we look at the moment of inertia in terms of kinetic energy. So suppose here is a mass object and its mass will be mi, and it is at a ri distance from this, and say it's moving like this, and say it is the velocity of this particle, particle, mass object, and say it is x-axis and it is x-axis, y and this is z-axis. So means it is rotating about z-axis. Now kinetic energy of this is given as, if it is a rigid body, then its kinetic energy is simply mivi square, and if there is such large number of mass objects in this body, then it is mivi square, or it is 1 by 2. And if it is a single object, then I can simply write down this as kinetic energy is equal to half mv square. It's for the rigid body, and it's for a single object when it's moving along the z-axis. So it is half mv square. Now this v is equal to omega cross r. So I am replacing this by r and this v by v simply, and this is by m for single particle case. So v is equal to omega r, omega cross r, and omega is along that axis and r is along xy plane. So that means this omega is perpendicular to r vector. So it is simply v is equal to omega r in terms of magnitude, because it's a square. So v square is equal to omega square r square. I can write down it in this way. So it is 1 by 2 m omega square r square. So half m r square omega square, and what to be called, this is known as inertia, I omega square. It's a simple way to look at this moment of inertia. So this I is equal to mr square is known as moment of inertia. But in later on I will talk about for different objects. We will try to find out the moment of inertia, but for that we will get different type of expression. So somewhere we will get 1 by 2 or 1 by 4 here, but I will talk about that later on. It's the simplest definition of moment of inertia. Now let me talk about next linear and angular momentum. Right, that's very important, linear and angular momentum. Sorry. So what is linear momentum? As generally we talk about that linear momentum is represented by p, and it is simply the product of mass and velocity. But what does it mean, the product of mass and velocity? It means that it is a quantity. Linear momentum is a quantity which tells us about, or linear momentum is defined as that how much motion is contained in a body of mass m. That's why I'm writing it as the mass into velocity, product of mass and velocity, right? So this is the simplest way to look at it. This what to be called as a linear momentum. Now I will define the angular momentum. So as clear from earlier slide that this mass is for the rotational motion, mass is replaced by inertia, or we call it as rotational inertia, and velocity is replaced by angular velocity. Right. So this is for the linear motion, and this is for the rotational motion. So these are analogous to each other in the linear and the rotational. So that means, as we have defined this linear momentum p is equal to mb, on the similar basis I can define the angular momentum is equal to I omega. Right, and this is the expression for angular momentum. Now we have to find out the relationship between the linear and the angular momentum, so that how linear and angular momentum are related to each other. So let me find out the relation between linear and angular momentum. This is again from the geometrical representation. We will have a look at it. Say particle is at a point r rotation vector is this, and say it is moving along this, and say it is the velocity of this particle, or I can say that it is a velocity, or momentum is also along the velocity vector, because momentum is equal to mb, right? So that means if I that means this r and this both are making an angle theta. So let us define, because here if I try to look at this x and y and it is z axis, so both r and p, they are in the xy plane, and this r and p both are making an angle theta with each other, let us say. And if I take their cross product, that means a new quantity is defined which is acting along z-axis or along the plane, which is acting perpendicular to the plane both containing r and p, and we call such a quantity as angular momentum. We call it as angular momentum, right? So this is a way to look at it, and this is the relationship between linear and angular momentum, right? So this L is equal to R cross P or R cross MB. So this is the required relationship between linear and angular momentum. And if I talk in terms of vector quantities, because R is also a vector quantity and P is also vector quantity, then we can think in terms of Cartesian coordinates. So in terms of Cartesian coordinates, if R is represented by xi cap, by j cap and z k cap, and this P vector is pxi cap, p by j cap and pzk cap, then this L is R cross P and it is simply I cap j cap, means in the determinant form I can write down it, and this is used sometimes to solve various numericals. So if I simplify it, then it is I, eliminating this row and this column now, and it is the remaining determinant, it is y py z pz minus j, right? It is x px z py plus k, eliminating this, so it is xy and px py, so it is equal to I cap, it is ypz minus zpy minus j xpy minus zpx plus k, it is xpy minus ypx. So it can be written as I ypz zpy plus j zpx minus xpy plus k. I just simply multiplied with negative sign and interchanged it. So that's it. It's a very simple trick which I am using. And y xpy minus ypx. So that means it has three components: lx I cap, l by j cap, and lz k cap. So it means different components of angular momentum can be written like this: ypx minus zpy, ly is equal to zpx minus xpy, and lz is equal to xpy minus ypx, right? So these are the different components, right? So that's all for this lecture, and in the next part of basics of rotational motion, I will talk about the torque, law of conservation of angular momentum, and law of conservation of linear momentum. And that's all for this lecture.